A very warm welcome to everyone present here today. Before beginning with the session, I would request you all to please take a note of the rules and instructions which are to be followed throughout the session. Everyone is requested to switch on your videos and to keep yourself on mute at all times, and the forum will be open for questions later. So kindly post your queries in the chat box also. William Pollard once said that without change, there is no innovation, creativity, or incentive for improvement. Those who initiate the change will have better opportunity to manage the change that is inevitable. Good afternoon to one and all present here. Today I am Priyanka on behalf of the Council of Shaheed Rajguru College of Applied Sciences for Women, University of Delhi, would like to welcome Dr. Jitendar Kumar Tiwari, the speaker for today's session. We would also like to extend our sincere welcome to all thoughtful and attentive audiences present here today. IIC, in collaboration with Instrumentation Department of Shaheed Rajguru College, has organized this session on the topic Process of Innovation Development, Technology Readiness Level, Commercialization of Lab Technologies, and Tech Transfer. We are honored to have Dr. Jitendar Kumar Tiwari as a speaker for today's session. So Dr. Jitendra is actively involved in innovative and quality research in the field of material science and developing a new class of efficient material through advanced techniques such as additive manufacturing. He has 7 years of experience in additive manufacturing of metals, alloys, and composites. He has also received CSIR Junior Research Fellowship and Senior Research Fellowship. We would now like to call and welcome Dr. Jitendra to enlighten us about the topic. Over to you, sir.
Thank you, Priyanka, for a nice introduction. So let me share my screen. Just 1 second. Okay, I think the screen is visible to everyone.
Yes.
First of all, I thanks to all who has joined this session, and I thank to the university that college who invited me to present the process of innovation development, technology readiness level. So I will share a few of the technologies which I have developed during my PhD and postdoc tenure. So I hope these technologies might not be related to your research field, but it will give you the intuition that how technology grows and what is the process of innovation. So those things I would like to emphasize with the help of this presentation. So as Priyanka has mentioned most of the things about me, that I am a material research person. So I'm interested to develop innovative materials like innovative composites, and I also play with microstructure of the material. So as you know about the additive manufacturing technology, so I basically work on the structure property correlation of that particular technology. So currently I am working as a DST inspired faculty in mechanical engineering department at IIIT Jabalpur, so which is a centrally funded non-profit organization. So this is just a quick summary. I mean, a lot of things had Priyanka already covered. So, but I'd just like to emphasize about my professional summary. So I did a lot of collaborations with these organizations, that RRCAT Indore, which is the body of Department of Atomic Energy, and UBC Okanagan, Canada. So one project I'm currently working with Professor Michael there, and Intech Additive. So I worked on the first indigenously developed metal 3D printer, which has been developed by the Intech Additive, as well as IIT Madras has contributed a lot for the development of this particular technology. So another project I'm working with, WPUT Poland, it's almost completed. Our collaborator is also in like KFUPM and NTU Singapore and CSIRM Pre. So I did PhD from CSIRM Pre. So a lot of technologies, which we have worked on during my PhD tenure as well. So this is my area of research, and these are the characterization and software techniques and methods which I have used during my research career. Just first we understand that what is the process of innovation. So basically, every kind of like every innovation just start from an idea. So when we experience a new need, then we just think to solve that particular problem, and then we just analyze the need of society and the marketplace, and then the research and development environment develops. So for example, if we talk about the development of metal 3D printer, okay, so it took around more than 100 years to reach the stage which we are now. So if we talk about like another aspect, like the different kind of aluminum alloys, like we are using in aerospace or automobile, lot of aluminum alloys we use. So this took around 200 years of consistent effort to develop these kind of innovative alloys. So any technology just need to go from these stages, like it's for first research, design and development, and then prototype production, and then it go for the manufacturing, and then marketing and sales. So marketing and sales is also very important aspect. I will give you one example. For example, if you see that Readiness, which is a 3D printer, it is a UK based company, and are already very well developed company for metrological applications. But the thing, it has not been established in India because of its weak marketing and sales strategy. Wherever the other companies like SLM Solutions and EOS, these have made a good market in India because of their strength in marketing and sales. So each and every pillar of this process is important. I mean, if you develop a good technology but you have weak marketing and sales, then obviously you will collapse somewhere. And if you have good marketing and sales but your product is not having a good strength, so obviously you will in initial you can sell people, but after feedback you will collapse somewhere. So we have to take care of all the things properly, and ultimately we must identify the need of the society. That is very important. So these are the TRL that we call as technology readiness level. So it depends on the task which have been assigned for a particular activity. So I took this particular literature from NASA website. So it is basically representing the development of successful missile operation. So how it grows, we are going to understand with these steps. So in general, all the technologies have these kind of steps. So obviously the terminologies will be different, but this will flow in this way. So the basic principles observed and reported. So that we also call is that it is kind of a literature review also includes in this TRL, because if we start developing a particular technology and after some time you realize that it is already been done by some people, so your whole effort will be wasted. So that you should be very careful about that. What you are going to work. So then you will develop a technology concept. So the concept is very crucial part, because if you see that many technologies which have a strong concept but weak infrastructure, but it grows consistently. So for example, if we talk about the intech additive, which has been developed indigenous system in India, like metal 3D printer, first metal 3D printer. But if we talk about, I mean, I don't want to criticize anything, but if we compare the software part of this particular technology with the foreign companies like EOS and other like Magic Software and all those softwares, then we found some weaknesses. But still, it is growing because there are there is, I mean, the fundamentally it is fulfilling all the requirements. So this is also very important, and I mean, analytical and experimental. So that we call as proof of concept. So in few more slides, in next slides, I will discuss that how we can we can also patent the proof of concept, or we can publish the proof of concept. So that I will discuss in upcoming slides. And so then I mean, once you will develop these kind of things, then you have to test it into the lab environment. So this requires a rigorous experimentation and manpower. You have to do a particular experiment many times, failing, and again, maybe after 100 attempts, you will succeed. So then, means these kind of things is very expensive. That's why most of the companies don't do that. So at that stage, we need the support from the government. That government support the research infrastructure in India to test the particular concept into the laboratory environment. So I mean, that is very important to investigate. Otherwise, we cannot move, as we can see that in TRL 5. In TRL 5, that is the component and a breadboard validation in relevant environment. So relevant environment, for example, if we talk about the any kind of missile, so I mean, it goes from maybe negative temperature to the positive temperature. Like it can go to the minus 30 degrees centigrade, or it can also reach to the 200 or 300 degrees centigrade if it is passing near to the sun. So I mean, that kind of conditions are there, but these kind of things you can test in laboratory environment, as well as you can also create a virtual environment for testing. So I mean, that is also, I mean, a real kind of test, because for a missile and all, you cannot I mean, you have to launch it directly. I mean, you cannot predict that what will happen after launching, but before, like, investigation, we perform some investigation, so that will give you idea that how it will react on particular condition, environmental condition. So like, there is demonstration, because you have to win the confidence of the audience, confidence of your customers. So even if you see the recent trends, so a lot of I mean, privatization is there in the rocketry part. So if you see, like, SpaceX in India, Agnikul Cosmos is the first company which is printing, I mean, that we call as a 3D printed rocket. So that is also got patented. So they are just following the path which already been done by the Elon Musk in SpaceX. But I mean, I would not say that their goals are different. But if we see that the growth of privatization in rocketry part, because initially only NASA or any department of atomic energy, or like DRDO, ISRO. So I mean, specifically ISRO did the launch vehicle and all those kind of things, but DRDO and other laboratories support them for the development of, for example, the material development or structural development or any kind of analytical tools development. Further laboratories support ISRO to function in that way. So then obviously you will go for these kind of testing, and then ultimately when you win the confidence of your customer, so then you can launch it, and you can I mean, you can just say confidently that yeah, this is the technology that is ready for the launch. So that this particular slide is almost similar, but I just want to specify that what kind of inputs and outputs are there that you can because most of the students have joined this session, so I would like to just tell you that initially you should not be very hurry for the technology. If you think, for example, people who are doing PhD, they just think that they can develop the technology within 5 years. So yeah, obviously some technologies can be developed in that tenure, but you should not be very hurry, because uh, if you see the literature of a particular topic, it is full of papers, full of concepts, full of kind of patents. So you need some time to investigate all those background. So it took around 2 years to build that kind of background. So then only you can just say confidently, yeah, that this is the gap I'm going to fill with my PhD. Or if you are working on a project, then you can say like that. So I must say that it took around 20 years, 30 years to develop a good technology. So few examples I will show, but these people are working from last 7 years, 8 years on those particular things. So I will just quickly go to those things. So this is the first technology which is already transferred to the Technos instruments. Um, just 1 second. I think yeah. So my voice is audible to everyone, I think. Okay.
Yes, sir.
Yeah. Okay. So yeah. So this particular work we have done in EMPRI, CSIR EMPRI Bhopal. So let me tell you first. Most of the people might know about the electroplating technology. So electroplating is already well established. Okay. So in case of electroplating, if we see, we have to cover a plate with another environment, another like material, for example, zinc coating or any kind of coating you can perform, so that it can protect from the other environment, like harsh environment or corrosive environment. These kind of things may happen. But if we guide that particular electroplating process in XY motion, that we can ultimately we can say that we can use this particular technology for the circuit design, or like we can say it as an electrochemical 3D printing process. Okay. So, and this particular diagram you can see here. So let me explain a little bit more about this. So it took around, I think, 3 years to develop this particular setup, and it is like already existing Ultimaker 3D printer is modified to develop this particular technology. So a lot of parts, as you can see, these parts are already polymer printed. So that we call as FDM technology. So you see, there is electrolyte and there is a metal rod, there is a nozzle, and then this whatever the metal rod will be, for example, it is copper, then the copper will be deposited here. So substrate, you can take some conductive substrate, like for example indium tin oxide. So once you deposit it, like you can make a circuit, or maybe you can make a substrate for SPR. This is actually basically Raman technology. So we get some enhanced signal from the Raman technology. So for example, if we use the electroplated substrate, then what happened? The basically the the signal we are receiving right now, the intensity of that particular signal will increase. So for example, if you are going to inspect any kind of, like for example, if any defense based system is there, or any kind of like suspicious environment is there, and you got very small sample. So for example, any accident scene are there, accident plate scene is there, and you got a very small piece of sample, and you don't know that what it belongs. So just you want the enhanced signal of that particular small sample. So that particular this particular technology can be used to enhance the signal with a small volume of sample. So it has tremendous applications. You can think of the applications of this particular technology in other directions as well. But right now, as I mentioned, two scopes. One is that you can provide the circuit design with this, and you can also use it for enhancing the Raman signal. Also, it can be used for the enhancing the other the spectroscopic signal. And this is actually the surface plasmon Raman spectroscopy. That is very famous technique for the Raman investigation. So plasmons is basically the collective oscillation of the electrons. So that is, basically these are increasing the signals. So we call as surface plasmons. Okay. So this is another technology. This particular work I have done in IIT Madras. So I contributed. The Dr. Murgian and Dr. Basil was working on this particular thing, and I contributed in the designing aspect and the printing aspect. So this particular part, as you can see here, this one. So this is actually forging punch. So this project was with Super Auto Forge. Super Auto Forge is a forging company in India, which contributes a lot in the forging of aluminium and steels, various steels. So this is actually took around 60 hours to print this particular object, and it was very painful. Because basically it is not straightforward to print anything like this. So before this, we perform a lot of investigation, because there might be some cracks, there might be some porosity in the printed material, so there might be some other defects. So you first investigate the material based on varying the laser process parameter. I think if anybody know much about the 3D printing technology for metals, you might have heard about the laser powder bed fusion process. So laser powder bed fusion process is basically, this is the system which already been developed by the Intech. So inside there is a inert atmosphere chamber is there where the printing goes on. So basically we take metal powder and we give some CAD design. So if anybody from the mechanical background maybe understand that if you give the STL file, we can print it. So this is not very, most of the people use FDM. It is very common now these days. So yeah, so let me just point out the innovative part of this particular technology, because there is no advantage if we, for example, this particular part we can make with the conventional manufacturing technologies, but why we are using additive manufacturing technology, that is important to understand. So what happened when we use this particular punch for forging application? This is already mounted in the real application. So it particularly hit the seats or the material various times. Like in 1 hour, it hits more than 1,000 times to the seats, and it got heated. So we need to extract the heat from here, and if you will not extract the heat, as you know, if you have some material science background, you will understand that when we heat any material, it got softened. So it will lose its strength. So the shape of this particular forging punch itself will get damaged. Okay, so what will happen? We need some cooling practice here. So we can just introduce some internal channels like this, horizontal or vertical. This is also a problem, research problem, that we must identify that which orientation is important, or which orientation is giving better results, and which is the micro, like the architecture of the machine or the system, which one is beneficial, so that we must understand. So I'll just conclude this particular technology, that we have designed the internal channels in this, the existing design of the forging punch, and that is particularly providing the cooling during the operation of forging operation. Okay, so this technology belongs to the Center for Futuristic Mobility, IIT Madras. So they have, I have other data, but I don't want to share here, because that is from Super Auto Forge. So some of the tests that Super Auto Forge company itself performed. So I cannot share those results. So this is, another very, this work I have done in IIT Madras, and just want to mention the innovative part of this particular work. So I personally feel that everyone knows about the microstructure, and the pole figure, and electron backscatter diffraction. So these are the terms you must know to understand this particular slide, because basically, for example, if we take a shaft, okay, we are using a shaft. So the shaft have like inner region and outer region. So for inner region, if we need creep resistance, so if we are applying it for like little bit higher temperature, so it needs creep resistance, and the outer region, it needs the fatigue resistance. So basically what is happening, the variation in the microstructure you need for the asymmetric loading. Okay, so for example, you are loading a particular object, so here load is different and here load is different, so you need varying microstructure also, then only it can sustain that kind of asymmetric load. So that is the innovative part of this particular work, that we are providing the functionally graded, that we call as a functionally graded microstructure. Okay, so there are three kind of functional gradation we can achieve. One is, you can achieve gradation in microstructure, you can achieve gradation in composition, you can also achieve gradation in porosity. So these three kind of gradation can be achieved with 3D printing technology. People have done it with the conventional technologies, but it is more feasible when we use laser powder bed fusion technique for metallic materials. So here I have utilized the parametric variation in laser powder bed fusion process, and achieve the variation in the microstructure. So basically, as you can see, this is a voxel based approach. So this work already published in materials letter, but I just want to emphasize a little bit more about it, that we actually divided the already printed sample in like voxel form. So each voxel have different laser energy density. So laser energy density, if we talk in simple terms, it is the amount of energy which we give for fusing the material. So it may happen that few people don't know about these terms, but I am explaining as much as I can explain about these terms, because you should have some background for the laser powder bed fusion process, then only these things, you will understand these things. Anyways, so just the idea is to vary the microstructure. So as you can see, these are the grains. Basically, these are the microstructure is varying. So that you can understand here. So apart from that, I also worked on another kind of functional gradation, as I was talking about the composition gradation. So you can also achieve the composition gradation. So I will just quickly explain why I'm going to achieve that kind of gradation. So that is very important to understand. And if we develop any particular technology, so we must know the what kind of research problem we are going to address. So for example, here you see, so the existing turbine blades, so in gas turbine engine or land-based turbine engine, we have turbine blades, and we also have lot of parts which are operated at high temperature at around more than 1500 degrees centigrade. So any kind of, like, any metal cannot sustain that temperature. Most of the metal will either get melted at that particular temperature, or it will get softened, or it will lose its strength. So to utilize the we need the ductility also, because it will also need this load sustainability. So for that, we perform some coating on the metal. So for example, if we talk about the Inconel 718, so this is the a type of nickel based super alloy. So this has around around 1400 degrees centigrade melting temperature. So if you are going to operate it at 1600 degrees centigrade, obviously it will get melt. So what we need to perform some coating. So that coating is any kind of ceramic. So that is yttria stabilized zirconia. Okay. So when we, and this BC is the bond code. Okay. So this bond code is basically used to address the thermal mismatch between these two materials. Okay, but obviously if we use, I mean, why we have thermal mismatch here? That is very important question to understand. So the thermal mismatch is basically this particular material has different thermal expansion coefficient, and this material has different thermal expansion coefficient. So when we increase the temperature, this will expand a lot, but this will not expand as the rate this particular material is expanding. So obviously it will crack. So if once it will crack, the environment, like the fuel burn here in this region, the fuel burn, if you use it for turbine blades or something like that, so it can damage the inside material. So those kind of things might happen. um, so to solve this particular problem, to address this particular problem, we need some smooth variation of the thermal expansion coefficient. So here you can see this is the thermal expansion value. So the thermal expansion value is almost same throughout the material, and obviously it will be same because the material is same. Then it is increasing like that. I mean, here it should have the straight line. I mean, if we for example, if we see the temperature, this is basically the temperature graph. But if we also plot a graph for coefficient of thermal expansion, so obviously with temperature, the coefficient of thermal expansion will also increase in general. So if you see here, so the in case of functional gradation, it will increase smoothly. So this particular single material of Inconel 718 will actually need the functional gradation to avoid the thermal mismatch. Okay, so that is the whole idea of performing this experiment. So I will not go much detail on these things because this is I think it might not related to your field, but I just emphasize about the research problem which we are going to address. So this is the schematic for the laser powder bed fusion process. So this is a dispenser where we fill the metal powder. So metal powder, like many people might surprise that why we are using metal powder, so, and how we can make it. So I mean, I would say that metal powder, it can be made by the gas atomization. Okay, so and then you can use to shape it in any way with the help of laser powder bed like laser powder bed fusion technology. So like we need some ball milling. So ball milling, I think everybody know about the ball milling. So we mix it these two powders, and what happened, these powders is actually YSZ powder is coated on the Inconel 718 particles. So that's how we get the sample printed. So as you can see here, This is basically having the functional gradation. So at the bottom side you can see it is little bit brighter, and when we are moving upper side it is little bit darker. So that is the composition gradation. So the YSZ percentage is increasing upside. So these are basically we are the performing the lab scale test. But in future, if we develop this particular material, we can also use it for like pipes or any kind of like in in exhaust section. We can use this particular material, or we can like there are there is one part which is like we call as a turbine entry temperature. So the turbine entry temperature, to increase that particular temperature, we need to increase the functional temperature of the material. So from the turbine to the exhaust, this section experience a very high temperature. Okay, so we must be careful, and we to use any new material. I mean, it's very difficult to convince the aerospace people to use new material as because they don't care what research you are doing. But ultimately, if you will not give a solid proof or solid things to them, they will not entertain your material into their system, because it's very risky. Okay. So there are some results. If you will be interested, I can continue explaining. So Priyanka, can I continue? How much time I have?
So we still have time. You may continue.
Okay. Okay, thanks for confirming. So, yeah, as I was discussing about the metal powder, so who is interested to be an entrepreneur? So basically, metal powder is having a big market now. Nowadays, there are few companies like Indo-MIM, Alpha Acer. These companies are supplying metal powders. Um, so Indo-MIM is the metal injection molding company, but they got certification for Inconel 718 to sell like over the globe. And there are other powders which they are supplying. I think they can also build on-demand LOI. So at least you have to order around 250 kg. So because gas atomization takes time also, and there is a category for AM grade powder. So AM grade powder means like additive manufacturing grade metal powder. So if you build around 250 gram of powder, only 50 kg of the powder will be of AM grade. That will be useful for the AM person. So the remaining powder is again go to the furnace, and like mixing or melting process occur, and then again they perform the gas atomization technique and to convert like them into the metal powder. But who is interested to start a new business? I personally feel that this metal powder is actually a big market, and it can like boost up, because if we talk about the binder jetting technology, which is a type of additive manufacturing technique. So the binder jetting is also used for the metals as well as ceramics, and I mean it is simpler than the fusion technologies like laser powder bed fusion, direct energy deposition, because it doesn't need any energy source like arc plasma source or the I mean the laser source. So because the laser is very costly, so laser is much more costlier than the arc system. So we must understand these kind of terms. Otherwise, if you will enter into the AM market, and you must identify that which technology is important, which technology has future. So there are few more technologies are upcoming. The research in India, it is at nascent stage. So you might have heard about the friction ester processing. So the friction ester processing is also can be utilized for the additive manufacturing technique. So so that we call as a friction stir additive manufacturing process. So very few systems are available. I don't think, in my knowledge, there is no commercial system in India for friction stir additive manufacturing process. So these are the things which we must know when we start doing any particular work. So basically, this is representing the DSC curve. So that is differential scanning calorimetry. The idea of performing this particular test is to understand the liquefaction behavior of the parent powder and the mixed powder. So when we mixed YSZ, as you can see here, these YSZ, these white color particles are the YSZ particles, and they are adhered on the surface. So basically what is happening, they will cover the powder particle, and the heat which is coming from the laser, that will not be properly transformed to the inside, like parent material in Col 718. So obviously the liquefaction behavior will get affected, and there will be partial melting of the metal powder. So that you can see here in the red color graph is representing the 4% yttria stabilized zirconia in Conal 718 mixture, and this black color curve is representing the Inconel 718, pure Inconel 718 powder. So what is happening basically here, you are getting deeper peak. So it is endothermic peak. It means it is absorbing the energy. So it is taking too much heat, and it is actually properly melting. So that's what it is representing. And why we have performed this particular test? Because as I mentioned, we are varying the composition. So obviously when we are varying the composition, we also need to vary the laser energy density. The energy which you are going to fuse the metal powder. So that's why the if you say like if you see in this diagram, it is little bit smaller. Let me zoom a little bit. So here you can see that I have varied the laser power as well. So here you can see this is actually fused at 300 watt constant laser power, but we have increased the 10 watt, 20 watt and 30 watt. So as we are progressively increasing the laser power here, we increase the rate of increment. So the fusion in this particular zone is enlarged view of these three figures you can see in A prime, B prime and C prime. So you can see the less number of cracks are available when we have increased the laser power up to 380 watt. So what it basically representing, it is representing that when you are varying the composition, you need to vary the laser power, and you must investigate the empirical relationship between the composition and the laser energy density. So you need to develop a relationship. So I must say that this particular test is not sufficient. You need to perform, for example, if you are varying the atrial stabilized zirconia up to 20% or 10%, then you must develop an empirical relationship, empirical relationship for the variation in the composition. So for example 0, 1, 2, 3, 4 and so on, and then you must identify that which particular laser energy density is suitable for which kind of composition. So that you must understand. So this is a microstructural results. I will not go much about I'll not discuss much about them, but this result is very important to understand, because this is representing that how we are going to avoid the thermal mismatch, which is already existing in the the turbine blades or any kind of high temperature application material. So this is the CT is basically the coefficient of thermal expansion. So basically what is happening when we heat any material, obviously it will expand. So why it is expanding? Because the lattice parameter is changing. There might be some phase transformation. So if we like it is changing from the, for example, in case of steel, if it is changing from the alpha ferrite to the gamma arsenide, and then it is changing to the delta ferrite. So these kind of phase transformation is there. So obviously, the based on the lattice parameter and its crystal structure is also important. So if it is transforming from BCC to FCC, obviously the packing will increase. So like these kind of things are there. So that defines the coefficient of thermal expansion. So here basically I must say that this particular sample is experiencing the lower thermal expansion when we compare it with the Inconel 718, because the yttria stabilized zirconia has lower thermal expansion value. So what is happening? It is affecting the coefficient of thermal expansion of the parent material. So around 6% decrement is observed when we are observing perpendicular to the composition gradation. But when we are observing, sorry, here we are observing it along the composition gradation, and here we are evaluating it perpendicular to the composition gradation. So here the variation is much more higher, because here the yttria stabilized zirconia, the equivalent composition of yttria stabilized zirconia is come in the picture. But here if you see, the individual composition of yttria stabilized zirconia is playing a very important role, and you might observe some fluctuation in this curve. So as I mentioned, that when we are increasing the temperature, obviously the thermal coefficient of thermal expansion will increase. Okay, so why it is increasing? As I mentioned, a lot of reasons like phase transformation and lattice parameter increment, all those things. But why these fluctuations are coming? That is very important to understand. In any kind of like, if you perform this particular test for different material, you might experience different nature. You might experience different these fluctuations. So basically, as I mentioned, there are a lot more metallurgical phenomena are there. So what kind of phenomena? Like phenomenon, that is first one is that is we call as precipitation. So this particular phenomena is happening due to the precipitation of gamma prime. So gamma prime is basically FCC structure, and it generally form in case of nickel based superalloy, and it formed due to the combination of nickel and aluminium. So the formula is Ni3Al, and this is the ordered structure. So the aluminium sit at the the corner positions, and nickel sits at the face centered position. So that's how the FCC contributes. Like nickel will contribute the 3 atoms, and aluminum will contribute as the 1 atom. So that the Ni3Al is the stoichiometry of the gamma prime. And then again we are getting the fluctuations. So basically I will explain, there is one more slide which better explain the exolution phenomena and other those things, that why there is a decrement in the coefficient of thermal expansion, and why there is again increment in the thermal expansion coefficient. So these kind of phenomena in the next slide I will explain, because I have done this particular test for the graphene LSI 10Mg composite also. So see, the material development is very tedious task, and it needs a lot of time. I must say, today we have transmission electron microscopy technique, we have atom probe tomography technique. Even I have done some atom probe tomography experiments of my material, not for Inconel but for graphene LSI 10Mg. I will show some results now. But material development takes time, because there is already a lot of material research is there, and people are now focusing for the alloy design. So if you see some background, like few companies have developed new alloys. There is called as Estel alloy. So for example, if we print aluminum series, aluminum 6 series or 7 series, it is having what we say, the hot cracking phenomena occur. So to arrest that hot cracking, we need to add some kind of crack arrestor, or we can say like it will create more nucleation point, and then it will avoid the hard cracking. So people added the scandium, and that's why we called as escal malloy. So I think, I'm not very sure, but this particular alloy is developed by the Boeing, which is aerospace company. I'm not very sure, uh, but that there is one aerospace company which have developed this particular alloy, and there is other alloy like wasp alloy. These kind of alloys have been developed recently. So, but as I mentioned, when I was discussing about the technology readiness level, I was discussing about the rocket engines. So any kind of aerospace activities doesn't allow easily to implement a new material, because it's very risky. So lot of test is required. So that's why I'm saying that material development takes time, and obviously if you are working for the high temperature materials, it takes more time, because high temperature materials are used for the critical applications. Anyways, so let me just conclude about this composition graded work. As I mentioned, there are three type of gradation. One is microstructure gradation, which I have already discussed in this slide, and then the second type is the porosity gradation. So I am currently working on that particular technique, but till now I don't have any results on that. But I will briefly summarize one thing, that like how with the help of laser powder bed fusion you can achieve the functional graded porosity. I will discuss about that later. But the third one is the composition gradation. So the composition gradation results I have already shown. These are the composition gradation results. There are much more results. So actually, yttriaxial zirconia addition refines the structure. So as you can see, the grain structure is refined after the addition of yttriaxial zirconia. There are some transmission electron microscopy results. So in TM, as you can see, these spots. So we have investigated these spots, and there is some proof of like formation of this. The lowest phase, which is unwanted phase. Uh, so we must avoid the formation of these phases, because it's actually it degrades the property of the material, and this is the EDS mapping. So that is we called as energy dispersive spectroscopy. So with the help of this particular technology, we can find out the elemental map, like the how different elements are distributed into your material. So for example, here I have added the yttria stabilized zirconia. So yttria is around 3%. So 3, we call it as a 3 YSZ. And so yttria is used for the stabilization of zirconia, and up to 8% the zirconia will fully stabilize. We call it as a fully stabilized zirconia. So basically we are adding yttria to arrest the transformation in zirconia, because there is transformation occur when we heat a simple zirconia. There is the crystal structure of zirconia changes. So after the addition of yttria, the tetragonal structure of the zirconia is it is like stabilized. So that's why we call it as a yttria stabilized zirconia, and that's how you can see. Here you can see that this distribution of zirconia. Okay, and this SSP is the solidification subgrain boundaries. So you know about the grain boundaries and the subgrain boundaries. So and yeah, this is very important to understand here. These are the spots which is we call as selected area electron diffraction. So the selected area electron diffraction is basically the diffraction pattern, like the electron beam is coming and interacting with the material, and there is a diffraction occur when it is got diffracted from different planes, and then it forms spots. So each spot is representing a plane. When sometimes you might have seen that it form a ring. So that particular ring is representing a family of plane. So if you read more about the selected area electron diffraction, so you will understand what are those spots and what it actually representing. Okay, so yeah, so this is actually the development of graphene LSite and MG composite. So I think everybody nowadays know about graphene. What is graphene? So this is a single layer. It is having hexagonal lattice structure. It is the I mean, if you take a single layer from the graphite, it will be graphene. So there are some like beautiful things for graphene. People say that it is having very high strength. It is 200 times stronger than the steel, and it is having very high thermal conductivity. Its thermal conductivity is around 5300 watt per meter Kelvin. For diamond, it is 2300 or 2200 watt per meter Kelvin. So diamond wafer or diamond is called as a very high thermal conductive material till now. So um, I mean, but people claim that graphene is having better thermal conductivity, 2 times higher than the diamond. So, and it is also having like very good electron mobility. So if it is having good electron mobility, it is obviously it will have good electrical conductivity. So it is also, having, I think, more than the silver. Okay. So there are these are the theoretical results that people share for the graphene, but in real practice, it is very difficult to measure these properties. Although after the successful development of like long graphene platelet, people have done some good experimentation to evaluate these kind of mechanical, electrical, and thermal properties of graphene. So obviously the graphene is very costly material because the synthesis is very costly. So if we talk about the CVD technique, so that is chemical vapor deposition technique. So in chemical vapor deposition technique, it is a build up, we called as a um, bottom to top approach. So actually we are taking a methane gas. So CH4 is a methane gas. So this the carbon from the methane gas is basically deposited on the silicon substrate, and it form a hexagonal lattice structure. So it form a single layer graphene uh, in the CVD setup. So this particular reaction happen at very high temperature, around I think around 1100 degrees centigrade. So this occur at very high temperature. So I'm much more emphasizing about this material because people use graphene for the electronic application, and most research is going uh, on the on the electrical part of, like, electronic part of graphene, because it is very costly, and it is having good, as I said, that electron mobility. So like for example, in like electronics application, it is widely used. But for structural application, people actually don't like to use graphene for structural application because the synthesis is very costly. But if we talk about the liquid exfoliation process, so who anybody who is working on graphene, they might know about what is liquid exfoliation process. So with the help of liquid exfoliation process, the synthesis of graphene is much cheaper. I would like to put one example here. As you see the development of aluminum alloys, so once, like, people were not knowing the formation of aluminum from alumina, the aluminum was much more costlier than the other materials. But right now, aluminum is much cheaper in comparison to the, like, for example, silver and all, because of the thanks to the Hall Herald process, so which converts the alumina to the aluminum, and that's how aluminum gets cheaper. After the development of that process. So similarly here, if we talk about the liquid exfoliation process, so the liquid exfoliation process is, significantly it reduces the cost of graphene. So right now, if you'll buy in market, like the multi-layer graphene, so there are various type based on the layer, like people call as a single layer, bi-layer, few layer, and multi-layer graphene. So the seller, they claim that we have this kind of things. So after TM investigation, you can find out that how many layers it have, or there is some Raman investigation that you can perform on graphene or any kind of carbonaceous materials. The Raman is very important characterization to understand the characteristic of carbonaceous materials. So yeah, so I was just telling that graphene is basically, it is not preferred for the structural materials, but after the development of these processes in future, we can predict that graphene can be used for the structural applications. So that's why I have developed a graphene LSite and MG composite. So this part of work is published in Additive Manufacturing Journal, Materials Letters, and Journal of Alloys and Compounds. So as I mentioned about you, that there was third kind of gradation, that is porosity gradation. So here, this is the synchrotron based X-ray CT. So people who are from the physics background, they must know about the synchrotron, what is that, and how we use it for X-ray computed tomography. So the tomography is basically, we are taking the picture in 3 dimension, and we are identifying the pores which is available inside the metal, and whether it is irregular pores, whether it is small spherical pores or big size spherical pores, that we must able to understand. So here we can see that the variation in the pores fraction as well as morphology. So the morphology here is irregular, then it is a small spherical, and then it is increasing. So so basically we can achieve this kind of gradation if we vary the laser parameter. So how we have developed this material, I'll just quickly explain that we mix graphene with aluminum, and then we do ball milling, and then we load it into the laser powder bed fusion system, as I already explained about the laser powder bed fusion technology. So in this way we can do some kind of printing, and then we find this kind of solidification behavior. So this particular material can be used for the low temperature heat exchanger. Okay, I'm not saying that it is already being used, but ALSI 10mg, I think around 1 meter long heat exchanger is already being printed with the ALSI 10mg. There is one, I think European company have already done this practice. So ALSI 10mg can be used for the low temperature heat exchanger application. Why I am emphasizing more about the low temperature? Because aluminum we cannot use at very high temperature. So in future, like if we talk about the Inconel and all, that we can use the laser powder bed fusion technology, and we can make big like for high temperature application heat exchanger. So this kind of technologies can be developed, but as I mentioned in the initial slide, that technology took around 20-30 years of development. So that's why there are various stages in any technology development, because if you are going to use a particular material, you must investigate that material, and the investigation of that material itself can take 2 years or 3 years. So then only you can going to use it for the next stage, and then again you will perform some analytical tools or other investigation you need to perform for the real practice. So that's why the role of material researcher is very important in any kind of technology development. So these are basically the characterization techniques which I have already used, and it is very important to know these characterization techniques when you are going to study the material, because you don't know the material, you cannot use it. So a very innovative result we found from this research, that when we add graphene into the metal and we fuse it with the laser, people say that it may happen that graphene can react with the aluminum and form aluminum carbide, or it can get evaporated, or it can get damaged. If you talk about the melting point of graphene, it is more than 3000, I think, in inert atmosphere. So obviously the temperature is not go up to that level, but there are possibilities that graphene can get damaged, or carbide formation, or it can it can just it lattice structure may change, and it can be found in the form of like a simple carbon. So that thing was actually, there was hot rationale in the literature, so that's why I have done atom probe tomography. So in atom probe tomography, as you know, that this is the high end characterization for investigating any kind of material at nano level in 3 dimension. So this is the first foremost technology for the micro graphical investigation. Okay, so basically, if you talk about the TM, transmission electron microscopy, so in transmission electron microscopy, you see around 50 nanometer layer, 50 nanometer thick layer, because that particular thickness is electron transparent, and you are seeing the 3D information in 2D. So that is the uh, idea of transmission electron microscopy. But if you want to see any information as it is, like it is in 3D, then we want to see at nanoscale in 3 dimension. So for that purpose, we can use atom probe tomography technique. And you can see here, this particular platelet is representing the embedded graphene inside the matrix. So this red color, I'm sorry, this is I mean, pink color is actually representing the silicon, and the other gray color is representing the aluminum atoms. So basically what happened, so this is the tip. So we form this kind of tip, and we place it into the sample holder. And what happened, a pulse laser will fall on this particular tip, and atom by atom, it is like every atom sublimates. So after the sublimation, what happened, the atom will attack, I mean, it will just fall on the detector, and based on the time of flight and detector position, we can reconstruct the 3 dimensional, I mean, structure of your material. So if we talk about the company name, I think the company name is Chemica. So the Chemica is the only company till now which is providing the APT services. So there are a lot more research is going on in the Oxford University for the enhancement of this particular system. But if we talk about the market of this particular technology, there is only two systems in India. One is in the IIT Madras, and another one is in ISC Bangalore. So the system which is available in IIT Madras, it is in collaboration with 7 other organizations. So for example, ARCI Hyderabad, IIT Bombay, IIT Roorkee, and some like other organizations are there, so which are using that particular technology. So it was actually established by Professor B.S. Murthy, which is a big name in the material science field. So he contributed a lot for the for the establishment of this particular technology in India. Okay, so there are some other results. So this particular work I have done in RRCAT Indore, this XPS analysis, X-ray photoelectron spectroscopy. So obviously we saw.
Sorry to interrupt you, sir.
Yeah.
Sir, actually, we are running out of time, so may I know?
Okay, I'll just quickly complete. Yeah, within 5 minutes, I will finish. Okay, so if you see that XPS results, so basically I have performed this particular results to understand that how the graphene is reacting with the matrix material, and that is actually spectroscopically it is proven that it is not forming any kind of carbide. And there are some mechanical properties which is very important to understand, that this fluctuation, I mean these variation, random results are coming because of the presence of porosity. So but if we compare the equivalent density samples, then we are getting around 21% increment in the yield strength. So these are the mechanisms which I told that the fluctuation, as I was mentioning about the coefficient of thermal expansion in the last slides, then I just mentioned that why these fluctuations are coming. So basically the exsolution of atoms are responsible for these kind of variations. So when, for example, it is a schematic, I'm not claiming the atomic position is correct here, but I'm claiming that the exhalation phenomena is responsible for the variation in lattice parameters. So if you see the mg atom size, so the size of mg atoms is bigger. So when it is situated in any kind of lattice, it is actually creating outward force to the corner atoms. And when it is extracted from that particular lattice, it will actually, other atoms will contract, okay, because it was pushing all the atoms outside. And here if it is having a small silicon atoms here, and then it is small, so it is attracting all the corner atoms at the room temperature. But when we are increasing the temperature, when it will go out, it will expand. So that's why these fluctuations are coming. Obviously the coefficient of thermal expansion will increase in general with respect to the temperature, but there might be some variation, and these variations are related to these exsolution phenomena. There might be some phase transformation also, but I will not go into that. So there I have attached some microstructures and all those things. So yeah, so I would like to acknowledge joining an additive manufacturing laboratory, IIT Madras, and like a sophisticated analytical instrument facility, SAF IIT Madras, and Triple MF Lab IIT Bombay. So if you want to perform any kind of FIB technique, like FIB test or like focused ion beam milling, and you want to perform EBSD test, or you want to perform like the residual stress measurement by XRT method, so you can approach to the Triple MF lab. There are TEM facility, new geol system is available in CSIR, Advanced Material Process Research, MPRI Bhopal, and there are some other rheological testing is available for the fluid, like fluid materials. And I would also like to acknowledge Intech Additive solutions, because around half and like 1.5 year I worked on the laser powder fusion system, which already been developed by the Intech. And I will also acknowledge the contribution of MCube 3D. So MCube 3D is the company which I started during the, I mean, my group started doing the PhD. So right now we are not like a very much big company for the OEM. Like we don't manufacture the metal printers, but we are good in providing the services for the metal printing services. And like for example, if you talk about the FDM, and as I mentioned about the electrochemical 3D printing, so MCube 3D is the only company in India which is supplying the electrochemical 3D printing in all over India. So there is no other competitor for that particular system. We are still working to improve that system. So with this, I would like to thank you all for joining this session. So actually, I mean, I must say that there might be some audience from different backgrounds. Some results was related to core material field, so that might not be related to the research field. But I would like to thank you for being patient and listening me. Yeah, so if you have any question, you can ask freely, and I am open for any kind of collaboration also if you want to do. Yeah, thank you.
Thank you, sir, for delivering such an amazing session. It was indeed very informative. Now, I will request our audience to kindly post their queries in the chat box, but they can also unmute themselves to ask their questions. All your doubts can be answered accordingly.
Meeting. So I'm stop sharing my screen, okay?
Awesome. Do we have any questions? So I guess there are no more questions. You explained really well to the students, and yeah, thank you so much, sir, for taking out your time. The institution's Innovation Council extends sincere gratitude to Dr. Jitendar Kumar Tiwari for taking out time from your busy schedule and joining us, sir. So this session has truly helped us increasing our knowledge about the topic. We extend our deepest gratitude to our principal, ma'am, Dr. Payal Nego, for being a pillar of support and strength. Last but not the least, we would also like to extend our heartfelt gratitude to the audience for showing your keen interest in joining us. We hope it provides you with great learning outcome. Thank you so much, everyone. I would request Dr. Jitendra Kumar and the core team of IIT to please switch on your cameras for a photograph.
Everything good.
I will request the core team to kindly switch on your cameras. Thank you so much. You may all leave now. Thank you so much.